This is, for us, Module 7. It's on acids and bases. It's a continuation of the solutions module because acids and bases are going to be aqueous solutions. Let's start with acids. Acids produce H+ ions in water. For example, when HCl gas dissolves in water, the HCl molecules will be broken by the polar water molecules. HCl is polar, and it will be pulled apart, and the two parts will be H+ aqueous and Cl- aqueous ions. So one way to describe these acids are they are proton donors. If you think of H+, a hydrogen atom has a proton and electron, so H+ is just a proton. They are electrolytes, so they will light the light bulb on a conductivity tester because they do have mobile ions, mobile electrical particles. Acid, the word acid comes from Latin acidus for sour, because all acids will have a sour taste. The H+ ion signals the taste buds a sour taste. They change different indicators, different colors, including litmus. They change red. Another property is they neutralize bases. Some common acids are the citric acid found in citrus fruits, the acetic acid found in vinegar, carbonic acid found in soda, and hydrochloric or muriatic acid found in concrete cleaner. So if you think of using a cleaner product to clean up after some grout work or some mortar work or some concrete work, the hydrochloric acid will eat away the concrete material. When it comes to naming acids, there's a few certain rules. First, let's start with the binary acids that only have two elements. Acids with an H and a nonmetal. They are of the form hydroic acids, hydrochloric for HCl. If you put H+ ions with a polyatomic ion, then the name of the acid is based on the name of the polyatomic ion. For example, if the polyatomic ion ends in 8, the acid's name will end in ic, followed by the word acid. For example, sulfate, SO4-2, makes H2SO4 sulfuric acid. If the ending is ite, you make the OUS acid, sulfite, sulfurous acid. I ate an acid, it was icky is one way of remembering that the ate goes with ick and the ite goes with us. So here is a large list of acids, their formula and their names. If you know your ion charges, you know that you always have as many H+ on the front of the acid as you have negatives on the negative ion, whether it be a single atom ion like bromide or a polyatomic like carbonate. You always match the number of H's to the negative charges on the ion. So HCl would be hydrochloric because it's binary. Hydrofluoric would be HF. HBr is hydrobromic. HC2H3O2. C2H3O2 is acetate, so that's acetic. I ate an acid, it was icky. CO3-2 is carbonate, so that's carbonic. NO3- is nitrate, so that's nitric acid. NO2- is nitrite, so that's nitrous acid. PO4 is phosphate, so that's phosphoric acid. SO4 is sulfate, sulfuric. SO3, sulfite, sulfurous. Now we move over to the bases. The ions that bases make in water, because bases are also electrolytes, are the hydroxide ion, OH-. So OH- is the characteristic ion of a base. They generally have bitter or chalky taste. They are electrolytes because bases will react with skin to generate a soap-like molecule. They feel soapy or slippery. and they neutralize acids are proton acceptors. In other words, OH minus can take H plus off of molecules, and that will make water, of course, and they turn litmus blue. And phenolphthalein, they turn pink. Phenolphthalein is colorless with an acid, but pink with a base. Some common bases. Bleach is a base. Drain cleaner is usually sodium hydroxide lye. Lye soap would be an example of a base. Bases with hydroxide ions are named based on ionic naming rules. Sodium hydroxide, potassium hydroxide, barium hydroxide, aluminum hydroxide, and iron 3 hydroxide. When you have an acid-base reaction, you're going to have reactants and products where one loses an H plus and the other gains an H plus. And so when the molecule has the H plus on it, it is considered an acid because it can donate that H plus. It's a proton donor. When it has lost its H plus, it's considered a base because it has the ability after losing to re-accept H plus, and so it's a proton acceptor. And so an acid and its conjugate base make a pair. So we say, for example, the reaction below is HA makes A minus. So HA is the acid, it's got an H plus it can lose. A minus is a base, it could gain H plus and form HA. So HA is an acid, A minus is a base. That's a conjugate acid-base pair. That's the first one. But the base, here represented as B, when it accepts H plus from the acid, it becomes its acid form. So B is the base form, BH plus is its base form, and so B and BH plus make a conjugate acid-base pair as well. So you typically have two conjugate acid-base pairs in every acid-base reaction. One pair is going to be the acid and base is going to have its acid form react with the other one's base form on the left side, but if it's going in the reverse direction, the first molecule is going to be the base form of the previous acid and then the acid form of the previous base. If we write the conjugate base, all we do is we remove H plus. So HBr would be Br minus, H2S, take away H plus, HS minus. H2CO3 is an acid, take away H plus, you get its conjugate base, HCO3 minus. Now you want to study this because this was not something we talked about in Chem 1. The conjugate acid of the base, NO2 minus, would be HNO2. You make a conjugate acid by adding an H plus. NH3's conjugate acid would be NH4 plus, and OH minus's conjugate acid would be water. Just put H plus onto the formula, add H, add a plus charge. If you've already got a minus, of course, that makes it neutral. Strength of acids. Strong acids are those that completely ionize in water. For example, HCl will completely ionize in water. Here we are showing a more expanded version of the HCl reaction in water. We've got HCl plus water making H3O plus. That's simply H plus attached to a water. It's called a hydronium ion, but you can think of H3O plus and H plus as interchangeable. Plus Cl minus. In that first reaction, HCl would be the acid, water would be the base, H3O plus would be water's conjugate acid, Cl minus would be HCl's conjugate base. But a weak acid will only dissociate slightly, maybe 1%, maybe 5%. This is seen by showing a double arrow, meaning that there's an equilibrium between the forward reaction and the reverse reaction. In strong acids, we only show an arrow to the right because the reaction does not reverse and have both of reactants and products at equilibrium. It only dissociates slightly. So here we have acetic acid plus water makes acetate plus hydronium. The acetic acid is the acid, acetate is its conjugate base, water is the base, hydronium is its conjugate acid. But the double arrow tells you it's a weak acid. These will not light the light bulb as brightly. Strength of bases. The strong bases are the hydroxides. The hydroxides from the metals of group 1A and 2A, lithium hydroxide, sodium hydroxide, potassium hydroxide, calcium hydroxide, group 2A has a double hydroxide on it. They dissociate completely in water, and so they are considered strong bases and strong electrolytes. There are some weak bases. Usually ammonia is the common example, but anything with even organic molecules with nitrogen on them tend to have this ability to be weak bases. They dissociate slightly in water, kind of like a weak acid, NH3 plus water. Notice the double arrow for equilibrium, meaning it's a weak base. Makes NH4 plus OH minus. These will not make as many ions in water. NH3 is a base, NH4 plus is its conjugate acid. Water is an acid in this case. OH minus is its conjugate base. So here we see water can play the part of an acid or a base. So water is an acid and a base. At this point I'm going to pause a little bit and insert a little Easter egg into this PowerPoint. So those that are watching this PowerPoint and actually viewing it, you have a chance at 5 more points of goal points. In order to get 5 points of goal points, all you have to do is copy what is on this slide right here. If you copy what's on this slide right here and turn it in at the end of Friday, when you turn in your other goal homework, you will get 5 more points of goal points just for viewing this video and seeing that you're watching my PowerPoint. So this is an Easter egg. It's only for those that watch the video. So keep it secret, and people have to watch the video to get the 5 points because they have to copy this slide down. Okay, if we think of water's formula, HOH, the H is H plus and the OH is OH minus, and so water actually has both acid and base properties. In fact, water can self-ionize to make H3O plus OH minus. The amount of H3O plus, or you could also call it H plus, in water determines the acidity of water. In an acid, you're going to have more H plus and less OH minus. In a base, you're going to have more OH minus and less H plus. Now the amount of H3O plus in pure water is very small. In pure water, 1 in 10 million molecules is going to be H3O plus, and the concentration is 1 times 10 to the minus 7 moles per liter. So it's a very small number of molecules that form H3O plus. But if you look at that 1 times 10 to the minus 7, that might look familiar because remember pure water has a pH of 7. The exponent 10 to the minus 7, the exponent is actually used to determine the pH. And so pH is a logarithmic function because it uses the exponent of a scientific notation number. So for example, 1 times 10 to the minus 10, 1 times 10 to the minus 1 molar, if that was the molarity of H plus, then that would have a pH of 1. 1 times 10 to the minus 2 molar H plus would have a pH of 2. 1 times 10 to the minus 3 molar pH of 3. 1 times 10 to the minus 8 molar would be pH of 8. So the pH scale, power of hydrogen, power meaning exponent, 8, capital H meaning hydrogen ion, the superscript of the hydrogen ion concentration is the pH. So if the molarity of the hydrogen ion is 1 times 10 to the minus 7, the pH is 7. 1 times 10 to the minus 1, the pH is 1. 1 times 10 to the minus 11, the pH is 11. Here's an example of a pH scale showing some common items and their pHs. You look at hydrochloric acid that we might use in lab as having a pH of 0, 1 molar. Your stomach fluid, 1.6, lemon juice, 2.2, and so forth. So a lot of foods are acidic, and that's what gives them some of their sourness. Then you get into water, which is pure water is 7. Most of the water people get from their tap is a little above 7 because of its contact with underground limestone. Blood is 7.4. Seawater 8.5. Milk of magnesia, a common antacid, 10.5. Ammonia is 11. Remember, it's a weak base. Bleach 12, and lye, Drano, 1 molar NaOH would be 14. Acids have certain reactions that you should know about. For example, acids react with carbonates to make a salt plus carbonic acid, and then the carbonic acid decomposes into water and carbon dioxide. So the overall reaction is acid plus carbonate makes salt plus water plus carbon dioxide. If you put hydrochloric acid on sodium carbonate, you'll get sodium chloride, water, and carbon dioxide. This would need a 2 in front of the HCl and a 2 in front of the NaCl to be balanced. Carbonic acid is very unstable, decomposes quickly, and so that's why we consider water and carbon dioxide to be the real products. Acids also react with hydroxides. That's an acid-base neutralization reaction. An acid and a base makes water and salt. They are double replacement reactions. If you consider the H from the acid pairing up with the OH from the base to make water, and the Na from the base pairing up with the Cl from the acid to make the salt. So here's the classic hydrochloric acid and sodium hydroxide making salt plus water. You might also see 2HCl plus calcium hydroxide making calcium chloride, a type of salt, plus 2 waters. Practicing balancing some acid-base reaction. Here we have HCl, which has only 1 H, and aluminum hydroxide, which has 3 OHs. And so we're going to need to triple the HCl to make 3 waters, and an aluminum chloride with 3 chlorides to balance out its charges. Here we have a barium hydroxide and a phosphoric acid. The hydroxides on barium have a subscript 2. The hydrogen on phosphoric acid has a subscript 3. So if we go to 6 waters forming, we need 3 barium hydroxides, 2 phosphoric acids to make the Ba3PO4 taken twice plus 6 waters. Here we have HCl plus a carbonate. This is actually sodium hydrogen carbonate. Remember, you make a salt plus water plus carbon dioxide, and it's balanced as is. Buffers. This is another topic we did not talk about in Chem 1. When an acid or base is added to a chemical called a buffer, the pH of the chemical will actually stay quite stable. However, if you add acid or base to water, the pH will change drastically. So a buffer is a chemical combination that will help to stabilize pH. For example, you need a buffer in your blood to keep the pH of the blood relatively constant. Buffers consist of a weak acid and its conjugate base, with the weak acid able to gobble up any extra OH- added, and a weak base available, the conjugate base available to gather up any H3O+ that you might add. This has the ability to neutralize acids and bases when you have a combination of a weak acid and its conjugate base. So in this picture here you see water at a pH of 7, but when you add acid to it, the pH goes down drastically, and if you add base, the pH goes up drastically. Whereas if the water contained a buffer, the pH would only change slightly from 7. So buffer solutions are going to be combinations of acid conjugate base pairs, and you can have a weak acid and you can have a salt containing its conjugate base, for example acetic acid and sodium acetate. Typically equal concentrations of the weak acid and its salt make the best buffers because they have equal amounts of weak acid capable of neutralizing added base and weak base capable of neutralizing added acid. They can also contain a weak base like ammonia and a salt of the conjugate acid, for example ammonium chloride. ammonia and ammonium chloride would be a buffer. Here's the acetic acid sodium acetate buffer. The acetic acid is the weak acid. The acetate part of the sodium acetate is the conjugate base. And so the salt is going to split up and give you that acetate ion and sodium ion. And so you've got the weak acid and the acetate in a large amount. If you add H3O plus, it will simply shift the equilibrium to the left, which will use up the H3O plus. If you add OH minus, it will simply shift the equilibrium to the right, which will produce more H3O plus.